So the screening mechanism that we're particularly interested in, or rather I was interested in during my master's degree, is chameleon screening, the chameleon screening mechanism. And this is a pretty interesting property. Essentially what it does is this chameleon field is a scalar field, so that's good because it means if it's got gradients we get forces, cool. But also its screening mechanism is the field values, or the field itself is suppressed, it's kind of hidden when it's around high density regions. So you're probably thinking, okay, cool, that's just a fun little fact. But no, what's cool about that is...
Hello and welcome to the podcast Matter Over Mind. My name is Stephen, and with me, as always, is Thomas. Hello, Thomas.
Hello. We're back for season 2.
We're back for season 2. Even better, we've got video as well, although you're breaking up quite badly just as we start. Never mind. But anyway, yeah, so we're back. We decided to go the whole hog and have video. We've moved YouTube channels now onto the Evil Sheep channel, which obviously the link will be there if you want to catch us. If you're listening on audio only, you can now see us talk as well. Who would not want that, Thomas?
Indeed.
So what's happened? No, not much. Not much happened since we last spoke.
Since we last spoke, I got married.
Oh yeah, there was that.
That was exciting. Married to your daughter, actually. So
that's right. Yes.
Yes.
So congratulations again. Yeah. So it was a lovely day. We had a lot of fun. How many weeks ago now was it? 3, 4, 5 weeks ago? I can't. I've lost track.
Yeah, about 5 weeks, I think.
About 5 weeks ago. So that was a lot of fun. Yeah. So we're both back at work now. I've actually spent a day in the training room today. First time for quite a long time delivering some training, and I'm absolutely shattered. So yeah, I hope I can get through.
Yes.
Now,
yeah.
We're going to talk about a topic I can't believe we didn't address on the last season, because it's actually a topic that you were involved in writing a paper, and we'll put the link to the paper on the show notes. But tell us about this paper that you wrote, or that you were part of, let's say.
Yeah, so during my master's degree, my sort of main piece of my master's work was towards investigating something called chameleon screening in cosmic voids. So this is a modified theory of gravity that proposes kind of like an additional fundamental force that may be able to answer dark matter and/or dark energy.
Yeah.
So
this is big. You know, this is all the stuff that people on the internet love to talk about. So we've got dark energy, we've got dark matter, modified gravity, something called chameleon gravity. It all sounds like, you know, it's kind of wacky and crazy. So we're going to get into that, and it's pretty exciting. The paper, I say we'll put the link up. Interestingly, there's another name on there that I recognise. Obviously, there's your name on the paper, but there's also Alan's name, who just happens to be my dance-off nemesis from your wedding.
Yes, that's true. You both had an epic dance battle to Darude Sandstorm. It was quite the sight.
That's right. Yeah, that's right. I'm very proud of that. So, Alan, if you're listening, you know, if you want to do a second round, you know, I'm here anytime.
Yes.
Right. Okay. So let's get into the topic. That's enough of that witty banter that we are so good at. Right. Okay. Let's talk about the topic. So you've written a few notes. You've sent me a few things to think about. I suppose from my perspective, how do we get there? How do we get to talk about this topic of modified gravity? Why are we interested in it? What problem is it solving, I suppose? Those are questions that are on my mind.
Okay. So, I mean, in general, modified gravity attempts to sort of bridge the gap that sort of regular general relativity can't quite answer. So stuff like, what is dark energy? Why is there excess mass that's invisible to us? All these sort of big questions that are somewhat up in the air on what the sort of explanations are. So I suppose a bit of a caveat, and I can get into this a little bit later on, it is essentially some theories of cosmology allow for there to be this dark matter, some light particle that's weakly interacting, that kind of congregates, and then add, sort of can explain things like galaxy rotation curves and stuff like that. So this is essentially, if you have a rotating disk, the farther out you go from the center of the disk, the slower your perpendicular velocity. But galaxies don't seem to rotate in that manner, which implies, according to the current ideas, that there must be excess mass on the outside of the disk to account for the shape of the rotation curve.
Right. So that's, if I can put that into layman's terms. So this is like if you spin a cycle wheel, if you measured the speed on the outside of the wheel, it would be going slower at any point than on the inside of the wheel. Is that right?
Yeah, that's right.
That's just normal physics.
Yep.
And so if you take a spiral galaxy that is itself spinning, you would expect that sort of general principle to apply. If all the mass in that galaxy was accounted for, you'd expect that the outside to go slower than the inside.
Yeah.
But it doesn't,
Yeah.
or not in the same way that you'd expect. So there's a kind of mystery there. And so one of the so it's basically, how do you account for that is one of the ways you might do that is through this modified gravity. And also, as I understand it, the way that the universe is expanding, that also hints at something else, some extra stuff in the universe that is making it more massive than we can see. Is that right?
Yeah, pretty much. So as the expansion of the universe, it kind of means there has to be some basically negative pressure that you might see if you look into it. But essentially, this is an expansion force, some force that's pushing everything out. Whereas you'd think if you have a balloon full of material, it will gravitationally attract, so it'll essentially collapse in on itself as the gravitational pressure works inwards. But that's not happening. We're accelerating outwards, so there must be this negative pressure, this external force, which is generally called dark energy. But again, what that is not understood. Yeah.
So we have dark energy, which is what you just described, and then dark matter is what we think explains the rotation of galaxies. Is that right?
Yeah, so that's just one of them. It's quite a common one that comes up. Also, some gravitational lensing. So this is where the gravitational field around a very massive object will bend the light, so you get these kind of weird distortions. In some cases, near large galaxy clusters, you essentially get more lensing than is accounted for by the mass in the galaxy cluster. So something has to be adding more lensing. So there's a few inconsistencies based on regular gravity that either implies there needs to be new mass or some alteration to our models of gravity.
Okay, brilliant. Okay, well, take us on this journey then. I know you've got a bit of a plan, so so do you want to kick off for us?
Yeah, so I should probably explain what gravity is before we start thinking about tweaking it and modifying it, right? Yeah. So in the simplest, when you learn physics at high school or university, the first thing you learn is Newtonian gravity. So this is very simply, there is a force that is proportional to the product of two masses separated by some distance. So essentially all that means is there is a force of attraction between two arbitrary masses at some distance away. So that makes sense. Basically, if you have object 1, it will be gravitationally attracted to object 2, and they'll fall in towards each other. Fine. And with that very simple principle, I mean, the equation's got like 3-4 terms in it, so it's quite a simple equation. You can derive a lot of stuff, actually. So you can derive pretty accurately the orbits of the planets using just this really simple model. So great. What's the problem then? Why bother doing anything more complicated? So there's one orbit that Newtonian gravity can't really explain what's going on, and that's the orbit of Mercury. It's got a pretty peculiar orbit. It precesses around one of its focus. So imagine you've got an oval, unlike a circle, which the centre is, well, obviously in the centre. If you have an oval, there are two focus, which are essentially, yeah, they're kind of like the centre, respectively, of an oval. There's some geometric property that defines it. But essentially, the focus are kind of 2 points that in somewhere in the oval, roughly central. So most orbits are elliptical; they're oval shaped, and they just kind of stay basically stationary. But imagine if you have an oval, and I put I hold down 30% into the oval. So now I suppose I decide to spin this oval around. So now the shape of the orbit of Mercury is also orbiting in a way. So they call it the precession of Mercury. So that's a little bit strange. And using just pure Newtonian dynamics, you can't derive that. That doesn't just happen. So for a while they thought up there must be, which this will be funny in the context of modified gravity. So they thought there must be some dark planet that we can't see or measure in any way that's pulling Mercury out of its regular path. And we'll call this dark planet Vulcan. Vulcan, yes.
Yeah. Yes.
So the dark planet Vulcan, which is invisible to us, and we can't interact with it anyway, is pulling Mercury around. So that's the kind of model they went with for a while. And I'm sure it got more complicated, but essentially, invisible planet with extra gravity pulling Mercury around in a peculiar way. So that was the plan for a while. That's what they thought was going on. So then, fast forward the clocks quite a bit, maybe 300 years or so, 400 years, and then Einstein comes along. And he derives his theory of general relativity. So this is essentially the current model we have of gravity. And I'll get into some more specifics in a second. And using this general theory of relativity, suddenly you don't need a dark planet Vulcan. He could accurately predict all of the orbits of the planets to very high precision, and the precession of Mercury kind of just fell out of his gravity description, and a bunch of other stuff as well. GR, for example, gravitational waves was predicted by GR ages ago, and we measured them in, I think, 2015 for the first time.
GR's general relativity, yeah?
Yes, yeah. So that predicted gravitational waves, which we detected in 2015, predicted black holes, which the first photograph was 2021, I think it was. Also gravitational lensing, it predicted a bunch of other stuff, and it's predicted it really well. So it's a very powerful theory that's done a great job. So I'm going to kind of talk a little bit now about what is, because general relativity, we're generalizing relativity, or what even is relativity. So that's kind of, before we go on, do you have any questions on what I've said, or are you happy?
Yeah, so let me just, first of all, I can't resist it because I love the word, but the English word mercurial means to be like, you don't know where you are with them. From 1 minute to the next, you can't predict how they're going to behave.
Oh, that's interesting.
And that's where we get that word from. Mercurial is from the word Mercury, because again, you couldn't predict where Mercury is going to be.
Interesting.
So I think that is superb, isn't it?
I didn't know that. That's cool. Wow.
That is really cool. It's one of my favourite words because of that. Anyway, that's by the by. All right, so you've got these two different ways of describing gravity. Newtonian gravity works most of the time, and sort of like conceptually, we think of it as like a force that draws other bodies to its body, if you like. So the bigger the object, the greater that force. But all bodies would have some attraction, if you like. And that's kind of how we think about gravity on a day-to-day basis. We think of it as a kind of attractive force, don't we?
Yeah.
But that's not really the way that scientists think about gravity, since Einstein, who came along with general relativity, and we think about it now more as bending space time, don't we? The fabric of space time. So these are two different models that generally come up with the same answer, but not exactly the same. So you're about to describe general relativity and sort of help me to understand what that means.
Yeah. So I should also caveat, you can get Newtonian gravity from general relativity. It's what's called a weak field approximation. Essentially, that just means a small scale or low energy limit to general relativity. Obviously, the term general means it's all encompassing, and you can get special cases from it. Hence, Newtonian gravity. So it all comes out in the wash. So they are So Newton is essentially an approximation of general relativity.
Got you.
Okay. So let's start off with special relativity because it started there basically. Now this is special, referring to special case. So this is a specific bit of relativity that then gets generalized. So relativity essentially is referring to two independent observers of a thing will view it differently dependent on how they're moving relative to each other. So if you're on a car driving by, you're stationary inside the car. You're not moving in the car, right? Mm-hmm. But so to you, the world is moving past you, but you're still.
Got you.
To an observer outside of the car, so suppose I'm standing outside the car, you're now moving, and the Earth is still for me. So that's relativity. It's how you perceive your surroundings based on what's called your inertial reference frame, or inertial frame, or frame of reference. So the caveat of special relativity is there's no acceleration. So either everything is stationary, or rather these frames are stationary, or at a constant velocity. And that's important because if you have acceleration, then you have forces, and then other wacky stuff comes into it when you start accelerating frames. This formalism allows you to define what's called a space-time. So within each frame of reference, you're going to have a different x, y, z, so different spatial coordinates. You're also going to have a different time coordinate. How you perceive time is different between reference frames. Which is why you get stuff like time dilation and what have you.
Got you.
Yeah, so which is why maybe you've heard that. I mean, we mentioned this actually in episode 1 of last season. Speed of light is constant regardless of how you're moving. So if you're on a plane and you fire a laser, the laser light isn't going the speed of light plus the plane speed. It's just going constant. So because you can now define a different coordinate system with different time, it makes sense to just kind of collate all those into one space-time. And now you can have a space-time. So you've got your x, y, z coordinates, your 3 spatial dimensions plus 1 time. So often how you'd write it is, for example, we would describe it as a 3 plus 1 dimensional system, the plus 1 being time.
Time. Okay.
Yeah. Cool. With this, though, you can define what's called a proper time. So this time is essentially the time perceived by a hypothetical observer at spatial infinity. So essentially, you're in your reference frame, you're in your car driving around, you have a different time, different spatial coordinates inside the car. I'm on the side of the road, similarly with a different time, different spatial coordinates. Well, how are these linked together? How can you even agree? How can you connect them? How can you say, who's relative to what? But now suppose you've got some character outside of the universe, infinitely far away, observing everything. They can essentially see everything, which means their time is the true time. Using that, you can then connect these reference frames and define stuff like time dilation and space dilation. Space contraction and all that kind of stuff. So this proper time. Okay. So using special relativity, or rather special relativity allows essentially to define a space-time, and then using that space-time, you can then derive a bunch of laws that I've mentioned before, stuff like path of least resistance, all that kind of stuff. But it's kind of shifted to a slightly different point of view. It's your trajectories in this space are the paths of shortest proper time. So it's just another way of saying conservation of energy, but you have to conserve this proper time, which is why the speed of light is constant between them all. Cool.
Okay.
So that's a special case. When you start accelerating these reference frames, once you start adding forces, then you can have multiple proper times, and it gets very confusing. But essentially, by adding
I understood it up on that point.
Yeah, me too. I remember in my master's year of university, I go to the class, my first class on gravity. They talk through special relativity. We're like, yeah, we've done this before. I know what's going on. And then he starts talking about Bob and Jenny and some rockets accelerating, and now they have different proper times. And I was like, hold on, this is all gone. This has all gone too far now.
Yeah. Okay.
But essentially what this means is, because you now have acceleration, you have forces of attraction. When you have forces of attraction, it essentially allows you to warp your space. So these forces, these gravitational interactions, you can view it as a force of attraction, but also you could view it as the space, as you said before, the space is warping and you're kind of rolling down the hill to meet your constituent mass partner. So when you do this, you can start predicting stuff like black holes, gravitational lensing, and all this kind of stuff. It just kind of falls in once you start, once you generalize to this frame where you're allowed. Also, I should have said a caveat of special relativity. Also, it's flat space as well, so it's essentially a local approximation as well.
Okay.
When you generalize it, attractive forces can warp, or rather masses can warp your space-time, and then you can have wacky stuff going on. Okay, cool. So we're all experts in relativity now.
Oh yeah, that's me. Expert.
Okay.
So this is kind of where I guess most people who know a bit about physics would say, right, we kind of got most of this tied down in a way. We've got some really good predictive laws or formulas that allow us to make predictions about what's going to happen, and over again, these seem to support general relativity. So we've got it sewn up. It's all sort of sorted.
Yeah. Okay. So where do the issues start happening? They start happening on once you start, zooming out and you're looking at cosmic scale stuff. That's when issues start arising. For example, the expansion of the universe suddenly can't be explained by regular gravity. You need to add in additional terms to account for this negative pressure, this outward force. Also, stuff like the additional lensing in galaxy clusters or galaxy rotation curves. Suddenly, this nice, neat model of gravity that explains basically everything, on a sort of solar system scale, starts to kind of breakdown's a bit of a strong word, but it starts to, the errors start piling up. Things are going wrong. So I'll kind of explain a little bit about cosmology. The theory of theory of expansion, our cosmological model, is essentially an extension to general relativity already. So the lambda CDM, or the lambda cold dark matter model, is pretty much the textbook one. So this essentially says dark matter exists. There is some hypothetical invisible particle that exists, and that accounts for galaxy rotation curves, excess lensing, etc. But also we have this cosmological constant. They call it a fluid. I don't really know why they call it a fluid, but that's what they call it. This permeating fluid that has a negative pressure such that we can now accelerate. And there are a bunch of issues with that, and it's kind of well known that there are issues, but it's the best we got. Essentially, this constant has been added in such that our current data matches the model, which, if you know anything about science, that's kind of bad science, really. You can't just...
Sounds like a fiddle factor.
Yes, and that's exactly what I would call it. Some people may disagree, but I think they're wrong.
Okay.
Yeah. So the issues with it, or one of the main issues, is if it's constant now, if you wind back the clocks, it's either too big or too small. I can't remember which one, but it's not quite right to explain earlier stuff in the universe.
This is the Big Bang. If we go back towards the early universe, which basically means it's getting smaller and smaller, in those early days, not long after it's banged, then it starts to break down. The predictions don't work with that same constant. Is that right?
Yeah, exactly. If it's a constant, it obviously doesn't change, right, by definition.
That's right. Hence the name, yeah.
But if you look at the data from back in the day and just plug in this constant, it doesn't match. So it conveniently only matches right now. Okay. So it's not great. It's not a great model. So there are these, I guess, modified cosmology models called quintessence models. And these essentially keep everything the same, but the constant is now time varying. So it can change over time. Nice and convenient, but, I would argue just as fiddle factory. But you've got a scapegoat.
You put another fiddle on top of the fiddle.
Yeah, exactly. And then there are these modified gravity models, which these make no assumption that dark matter is real, and they essentially say that perhaps general relativity is an incomplete theory. It was derived like 100 years ago. Maybe Einstein didn't think of everything. Maybe. And this is the kind of school of thinking I'm in, right? If you take classical mechanics, the physics of our scale, if you go smaller and smaller and smaller, suddenly quantum mechanics has to kick in. You can't use classical physics to describe quantum phenomena. So if you zoom down far enough, suddenly our normal physics, our classical physics doesn't work anymore. My idea is perhaps it's the same if you go up. The bigger and bigger you get, maybe there's also a point at which suddenly these extra stuff, these extra phenomena start occurring that classical models can't account for. That's my idea. There's no textbook that says that. That's just my opinion. It just seems to make sense to me. But yeah, so modified gravity. So I'm going to talk a little bit about what that even means. How do you modify gravity, right? Okay. So within the equations of gravity, the Einstein's field equations, there's this term called the Ricci scalar or Ricci scalar. Essentially, it's the term that governs your local geometry, or not necessarily your local, but it determines the surface of your space-time. And that's this value R. One of the simplest ways to modify gravity, not including something called MOND, which I'm not going to talk about because I don't really know anything about it. So I'm purely talking about MOG, not MOND. So anyway, one of the ways you can alter the equations is, instead of having just this scalar, this Ricci scalar, you make it a function of that scalar. So what that means is, suppose I have some equation that tells me how the temperature changes over time, say. Instead of saying, okay, if temperature increases by 1 degree, this thing increases by 1 unit, I can say, okay, well, suppose I have some combination of temperatures kind of boxed in this function. So I put something in, and then all the different, it could be like temperature squared plus 3 temperature, say. So it's some function of temperature instead. So that's kind of what you're doing with this curvature. Instead of saying this is the curvature, you're saying it's some function of the curvature that could in principle change. So you're essentially generalizing general relativity, and this is called F of R gravity.
Okay.
So it's a fairly common thing. If you have some function of a variable, it behaves differently to just the variable by itself. So F of R gravity. You generalize general relativity by implying maybe the curvature isn't fixed. It can vary. Okay. What you can do with this is now again, I won't explain how you do this because there's a bunch of complicated maths, but you can map it to what's called a scalar tensor theory. Essentially what this means is, without breaking the rules of maths, the objects within it, you can kind of say there's something else, and that's fine. It sounds like a bit of a cop-out, but how do I think about this in a way that's more satisfying? Okay, so any of you computer folks out there may know what I'm talking about. If you have an array, a list of items, that in itself is just a list of items, right? If you transform it into a vector, then suddenly each of those items the list can now be treated as an object instead of just a list of items. For example, if you have a speed, if someone's like, here's a list of speeds in X, Y, and Z, okay, you can't really do a lot with that. But if you have the velocity vector, now the number occupying that same space is the same, but it tells you the directionality, right? So a speed is just how fast you're going, a velocity is how fast in what direction. So that's a bit of an example of how you can basically use a list and then transform it into a vector and get slightly more information without really changing anything.
Okay.
That was a bit of a hand-wavy explanation, but just trust me.
Okay.
Okay. But anyway, the punchline was you can generalize general relativity by treating this curvature term as a function of the curvature as opposed to just what the curvature is. Okay. There we go. Okay. How was that?
Yeah. Okay. So I think a lot of us will be a bit lost on the maths on that, but I don't. I think there's limits to how you can explain that to us without understanding the maths. So I guess if you're listening and you understand that side of things, then you're with us. If not, we're just gonna have to accept your hand wavy explanation for now, and I'm happy to do that. So we can move on.
Yes.
But basically, what we're saying is that using a mathematical process, you're able to generalize general relativity, which allows us to do what? So let's take it from there.
So just before we move on, I'll put a little cartoon on the Facebook page of what I'm talking about.
Okay.
Of the variable.
Right.
Transforming into a function of the variable. So just so you folks know what I'm talking about. Okay.
Right.
Yeah. So what can you do with that? Okay, fine. So now you've generalized general relativity. Within the equations, there's terms that tell you about the curvature. That's on one half of the equation. So that, the geometry of your space-time, and then the other term is your matter. And it's contained in this matter Lagrangian. So if you remember from the Lagrangian episode, you essentially have an energy balance to do with interacting matter. Fine. So in the base equations, you just have your normal matter species and you have your kind of fixed curvature. I'm using fixed in inverted commas here, just regular R instead of F of R. And then you can kind of explain, okay, well, what happens to the curvature when I have this mass and so on. Fine. But when you generalize it, you can essentially add in these scalar fields. And if you'll remember from the speed of light episode, scalar fields have an important property. A scalar field, for example, is like the electric field. That's an example of a scalar field, or rather the electric potential is a scalar field. So if you remember when I said you have a field, if you have a gradient on that field, the ball can now roll. I have a ball on a hill. It can roll because there's a slope. There is a gradient, therefore a force can act. So by mapping f of r to what's called a scalar tensor theory, you can essentially add in scalar fields without breaking the rules. And if you have scalar fields with gradients, you have a force, extra forces. And from these extra forces, in the equations of gravity, it kind of pops out, oh, now there's extra stuff that can potentially explain stuff like the expansion or, potentially extra accumulation of matter and so on. So basically, by just taking general relativity one step further, it just fools out that then you can have these extra terms that add extra forces or extra interactions between the matter.
Okay. All right. So I might be jumping the gun here, but if that's the case, doesn't that, because we've kind of got that all understood, or if we start now adding extra terms and start adding extra things into the equations, isn't that going to mess up what we kind of already know about what we've got?
Yeah, so I mean that's a good point, right? If you start, if you have an equation that describes how things attract or repel each other, if I start adding a bunch of stuff, it might mathematically be allowed, but isn't that going to alter how these things, like I said before, we've very accurately can measure the orbits of the planets and a bunch of other stuff. If we add extra forces, surely that's going to be different. So that's where comes screening mechanisms. That's where screening mechanisms come in. So explaining what a screening mechanism is, if you Google it, it kind of gets confusing because everyone has a different definition of what it is. Essentially what this is some property of the thing kind of hides it. So for example, telestatic, if you're far enough away, it's just a grey sheet, right? You can't see any structure in it. It's just, background noise. If you go really close, you can now see the individual pixels. You can see the kind of salt and pepper of the screen. Okay. So when you're locally within a region, it has some structure. When you zoom out globally, it's lost its structure. It's self-screened. You have the screening mechanism there, I guess, is the eyeball's resolution or the ability to distinguish between two close objects, right? So that's an example of a screening mechanism. In plasmas, you also have a lot of screening mechanisms. So a plasma, if you recall from a few episodes ago, is just an ionized gas, a gas that has electrical charge. But one of the key properties of a plasma is it has to be what's called quasi-neutral. So external to the plasma, it has to, on average, be neutral. It can't have a net charge. But obviously, if you have charged particles whizzing about, they permeate an electric field. If you have an electric field, like charges repel, opposite charges attract. So what's going on? Essentially, you can define a radius or a sphere that says anything behind that sphere, all the positives and all the negatives cancel each other out. So you just have ambient background. So that's another example of a screening mechanism.
Okay. Yeah.
So the screening mechanism that we're particularly interested in, or rather I was interested in during my master's degree, is chameleon screening, the chameleon screening mechanism. And this is a pretty interesting property. Essentially what it does is this chameleon field is a scalar field, so that's good because it means if it's got gradients, we get forces. Cool. But also its screening mechanism is the field values, or the field itself is suppressed, it's kind of hidden when it's around high density regions. So you're probably thinking, okay, cool, that's just a fun little fact. But no, what's cool about that is, I said before, solar system scale, general relativity explains very well. But the solar system has a lot of mass in it. The sun's pretty heavy, so are the planets, and there's a lot of matter. So we want to modify gravity without interfering with what we've measured. So screening mechanisms are great here, particularly screening mechanisms that hide themselves or that allow the field to be hidden in high density regions. So the solar system I would consider a high density region because there's a lot of stuff with a lot of mass. So locally in the solar system, the density, or the idea is the density is high enough such that the chameleon field is suppressed, and the chameleon field is suppressed low enough that the chameleon force doesn't have an effect on this scale. It's negligible. It probably still is there, but it's so small you won't notice it. Therefore, it doesn't affect our current predictions using regular general relativity. So, a bit of a get out of jail free card there, screening mechanisms, because they're kind of, I mean, like there are many, but the chameleon one makes more sense in the context of gravity, just because
Okay.
yeah, we know how things behave on a scale, and we need it to not affect that scale. So if you have a mechanism
Yeah.
that hides itself when there's heavy stuff, then it doesn't affect these things.
Okay. So let me just play this back to you. So what you're saying is basically there's this, let's call it extra force, this other
Yeah.
thing that this is hypothetical. We're not saying, you're not claiming that you know this to be true.
Yeah.
This is the theory. But if this field is there, then it's everywhere. But
Yeah.
it's not. It doesn't interact in areas where there's high density. By high density, you mean even things like the solar system. So
Yeah.
how really really low density regions, then you would start to see this effect that the chameleon field would be responsible for. You're not going to see it at this level, so we're not going to see it around the Earth or Mercury or anywhere around here. But if you start getting into big sort of scales, then this is where you might predict it, and obviously in theory you could then start to observe it. So how big a scale are we talking about?
So it turns out, I mean, people are kind of looking for chameleon on all scales. I mean, there's some people doing research into the quantum chameleon, but in the context that I've investigated, we were looking at cosmic voids, the universe's most underdense regions. So these are probably the biggest structures in the known universe. So if you've heard of the cosmic web, this is essentially, if you zoom really far out, you know, suppose you are this observer at spatial infinity, you might see it. And this is where, imagine you've got like a cotton wool ball and you pull it apart and you have a bunch of these filaments kind of connecting. So those filaments is where the matter lies. So a bunch of these galaxy clusters kind of form this web-like structure. The space in between those are effectively empty. They're voids. So these are what are cosmic voids. I mean, the size of these things, you know, some of the super voids, you get, you know, radius of, or radii of maybe 30 to 60 kiloparsecs, or megaparsecs, sorry, which is, well, I don't, Google what a parsec is, and now times it by 60 million. That's that. So
how big compared to like the Milky Way? How many Milky Ways roughly would that kind of be?
Let's see. Let's have a quick Google. So the Milky Way is about, let's see. Okay, so the Milky Way is 30,000 parsecs in diameter, allegedly. Okay. So that's pretty big. So times that by 4,000. So 4,000 Milky Ways side by side, but in a sphere. And there are loads of these things. God. These things, basically,
these are the voids.
These are the voids, the cosmic voids. So yeah, I mean, you could travel for billions and billions of miles before you even saw anything. These things are kind of almost scary, to be honest. Cosmic voids, they're so there's just nothing for billions and billions of miles. This sort of rough density of a cosmic void is about 10% of just the ambient background. So the ambient background is the average density if you average everything in the universe. But obviously there's a lot of empty space in the universe, right? So if you average that, it's 10 times smaller than that is the average density inside this cosmic void. So basically nothing there, and they're absolutely massive. Yeah. So
on that scale, then the theory is that this is where you'd start to see measurable effects down to this chameleon.
Yeah, I mean, because like I said, if it's hiding itself when there's a lot of stuff, go to the place where there is nothing, and then in principle it won't hide itself anymore, and it will be at its maximum value. There are some subtleties and caveats to that, but yeah. So this was kind of the punchline of the paper, I guess. This we're investigating a hypothetical acceleration experienced by a test particle if you are in a cosmic void. So
I'm just gonna say something here. Not to be critical, but I found that there wasn't really a punchline in the paper. That was the most disappointing bit. So the papers I'm used to have a conclusion at the end, which says, based on this, this supports X or this supports Y, and we need to know more about this and so on and so on. But there was nothing like that. It's a whole complicated bit of maths, and then it kind of left me hanging. It was a bit like an episode on Netflix that is cancelled, and I never know what's going to happen.
Yeah. So in forgiveness of the paper, the purpose of the paper wasn't necessarily to solve dark matter. It was to propose density profiles of cosmic voids and basically try to maximize this hypothetical force on a test particle and see how it behaves with different density profiles. So a bit more boring than I've kind of hyped up there, but what I will say is in my master's thesis, which kind of goes a little bit further than this paper, there is a bit more of a how this could be useful. What I might do is I might on the Facebook page upload a PDF of my master's because I can, and then people can read at their leisure if they so want to.
It's a good time to mention that if you're not a member of the Facebook page, then or Facebook group, I should say, then by all means do so. It's called Matter Over Mind, and it's just an open to anyone group. If it starts to get a bit spicy, then I might require that people ask for access, but at the minute it's open access. So join us, and you can see some of the pictures and stuff that we put up there to help explain some of the episodes.
Okay. So where great. We've sort of we've proposed an addition to gravity that doesn't break the rules. It's just a natural extension of the maths. And we've added this new field, and I should say we've added a field. What I actually mean by that is because we're proposing a fundamental force. There's four that are agreed on. There's gravity. There's electromagnetic force. So the attraction between charged and magnetic particles. And then you've got the strong and weak nuclear forces. So the strong nuclear force allows atoms to bind together, and the weak nuclear force governs interactions of subatomic particles. So those are the four well agreed upon fundamental forces of nature. What fundamental means is there is no building block of that. It's not this force comes from this thing. That is the bedrock. There is nothing beneath that. There is nothing more fine than that. That's the fundamental force. So these fundamental forces, so adding a term to the field equations, what we're really doing is when you generalize it and map it to the scalar tensor theory, these scalar terms come out that have the same form as a Lagrangian. It's a kinetic term subtracting a potential term. So it kind of gets grouped in with the matter Lagrangian. And why this gets grouped in with the matter Lagrangian, and the matter Lagrangian is just the energy of the stuff, the energy of the particles and the matter. Because it's strongly coupled to the matter, so the screening mechanism is such that if there is matter, the field suppresses, and if there's no matter, it amplifies, but doesn't screen. And it's a fundamental force to do with that. It's kind of just wrapped up in the matter Lagrangian. So you're not really adding something, it's always there. But so I should caveat that. You can add stuff, but I complained about that earlier on, so I should caveat this is slightly different. So this particular fifth fundamental force, or this modified gravity force, this chameleon force, it essentially opposes the pull of gravity. So that sounds counterintuitive, but if you think about it, kind of, you take some sort of logical steps. If it hides itself when there's heavy stuff and comes out when there's no stuff, you could kind of intuit that maybe its force, its gradient increases as stuff decreases. So basically the gravity opposes the chameleon force. And this is not too dissimilar to the cosmological constant with its negative pressure. It needs to be opposing gravity to cause some expansion. Fine.
Yeah.
So when we were looking into these cosmic void density profiles, we proposed a few what are called toy models. So these are kind of oversimplified versions of what you might actually see, just so you can then do mathematical analysis on them without getting too complicated too quickly. And what we found, now this isn't in the paper, but this is in my master's thesis, that there's a term in the equations of motion of the chameleon gravity that it's strongly dependent on density gradients. So what we found is the place that maximizes the chameleon force are when you have void mergers. So these are when you have two cosmic voids very close to each other. I guess kind of colliding is probably a bit too exciting of a word to use, but merging, I guess. So where you have extremely underdense regions directly next to extremely overdense regions. As these voids are merging, you can imagine the filament between the voids squeezing together, so ramping the density up. So that's why you have the maximum chameleon field close to this edge, this spike in density.
Okay.
And we kind of calculate some values or some strength of this chameleon force. So, I mean, it turns out, at least according to this analysis, that maybe the force isn't quite strong enough to explain cosmic expansion or dark matter. But what it could do, and this is something actually that is close to my heart, because this was my initial PhD proposal that ended up not going anywhere.
Okay.
So my thought was the chameleon field or chameleon force, this fifth force, counters gravity, which essentially would mean that it would slow down the growth of these cosmic voids. So cosmic voids, they're space in between material. Material gravitationally attracts itself, so everything kind of squeezes and tightens up, which means the voids get bigger. Fine. But if the chameleon force does exist, then it would counter that. Now the chameleon force is very weak, so you wouldn't see it over small time scales, but cosmic voids evolve over cosmic time scales. I mean, these are extremely old, long-lived things, right? And also there's a lot of them. So what it could imply is it could alter how large-scale structure forms in the early universe. Thus, it could affect how... So how do I say this? It doesn't affect the age of the universe, but it could kind of slow things down. So maybe we're living in an older universe than we think because we're not accounting for the slow, the decrease in evolution speed, for example. So this is kind of the conclusion to my thesis. Is a thing to look into next would be, okay, well let's investigate large-scale structure formation over cosmological timescales and see if there is a statistical effect. So the force is small, but if it happens over a long enough time to enough things, you get some statistics on it, and you might be able to tell a difference with chameleon gravity turned on or off based on how things grow and expand. So that's the slightly more exciting implications.
That'd be interesting.
Yeah.
So if that hypothesis is right, then the universe is older than we think because we've been calculating it based on the gradient that we think we can sort of turn the clock back and think about how big it was back then. But we're not accounting for this stuff, or this force that you're describing. Wow.
So this kind of research, the large scale structure formation and fifth forces, Queen Mary, University of London, that's research that they're doing, and there's a few others. Nottingham, for example, a researcher called Claire Burrage is an expert in screening mechanisms, and she was my supervisor's
She's not
boss
of the
when I
authors.
did this.
Ah, right.
Yes.
Okay.
Yeah.
Yeah.
So she's done a lot of stuff on dark matter and these screening mechanisms. So it's very interesting. It's very theoretical. Well, there are some laboratory tests for it, but this kind of stuff, the cosmological side of it, is quite theoretical. So it's fairly niche. Modified gravity doesn't really get talked about all that much, but it is interesting. I do find it quite interesting.
So if that was to, we don't need to get into it in too much detail because we're coming to our hour, and I think we've probably covered as much as most people can take. Certainly me. But if that was true, so if we find more evidence for it, and if it becomes, an accepted sort of thing that we think's happened, what implications would that have for things like dark matter or dark energy and those sort of what implications would there be? Would it affect, unlike the cosmological constant, would it affect that as well?
Possibly, yeah. Some of these, like I said, the chameleon field perhaps is too weak, but yeah, some of these, I guess, more robust modified gravity models, it could, if a good enough theory comes out that then gets experimentally verified, in principle, it could say dark matter isn't this invisible particle that's hard to engage with. It could just not be real. It could just be, actually, gravity has this extra term that we didn't realize. Now that explains everything. So it could explain away a lot of the mysteries. And the dark energy thing, the expansion of the universe, it could explain either it is a negative pressure, it is this fluid, or this. And if we know how it expands, and we could, there's a lot of theory on how inflation works, which is kind of undecided, because obviously we can't wind the clock back. Basically, you wind it back up to the end of inflation, but if you keep winding it back, you get some errors start cropping up. But if you know exactly how the universe's expansion and by what mechanism, then maybe you could accurately wind back the clocks. So if these modified gravity theories do come out and win the race for the answers, then it could explain a lot of stuff. It could solve a lot of mysteries. And a big proponent of modified gravity that I'm a fan of, or rather a thing that I like about modified gravity, is a lot of them try to be what are called model independent or theory independent models, or model agnostic theories. And what that means is, in principle, I could write an equation that explains everything we see. Now, there will be no grounding in it. I've just written down a bunch of maths that happens to fit the data. That's not really a good theory. That's just speculation, and you got lucky. It doesn't tell you anything about the system. What a lot of these modified gravity theories try to do is derive a theory from the ground up, basically. From small scale. Can we test this in a lab? Can we observe this directly? Yes, cool. And now let's expand on that. If it's a good theory that truly describes what it says it describes, it should work at all scales. In the same way I said general relativity, if you lower the energy, you get Newtonian gravity, which we know works. In principle, this modified gravity theory, this all-encompassing theory, should be able to. General relativity should fall out of it, and from that, Newtonian gravity should fall out of it. But you need to be built up from the ground up. Also, with Chameleon, like I said before, quantum Chameleon is a thing people are looking into, because obviously quantum gravity is a big question, right? So that's why I like modified gravity. A lot of them try to start from the ground up instead of just tacking on terms to an equation that already exists.
Cool. Okay, so I suppose we should say that it's a minority view. Most physicists seem to be quite happy with dark matter and dark energy, or at least their kind of their research is based upon that. So I was listening to this podcast about this topic, and they kind of started with the physicist there talking about all the emails he gets from people saying, "I've got this. I know. I understand the theories of gravity, and you've got it all wrong. These are the theories, and there's sort of various variations of modified gravity. But we're not talking about wacky ideas here. We're talking about proper physicists doing physics, carrying out experiments as well, or having, setting up proper ways of testing this stuff. So that's what you're interested in, not kind of crazy, wacky ideas that come at the top of your head.
Yeah, exactly. Yeah. It sounds kind of sci-fi saying modified gravity, but yeah, there is a method to this. It isn't just coming up with any old nonsense and being like, wait, what if the gremlins in the sky are messing with things?
I think part of the problem as well, chameleon gravity makes it sound like it's a kind of almost like it's hiding, and it's not that it's hiding, it's just that it's not visible in certain, if it's true, it just means that it's our ability to identify it is the problem, not that it is suddenly trying to be sneaky and hide from us. It's just whether we can see it at certain times and places.
I mean, if you look at the maths, the mass of the field doesn't suppress. So I said high density suppresses the field value. The mass of the field, so the matter of the field, that doesn't go away. That stays constant. That stays fixed. How heavy it is essentially stays fixed. It's just how easy it is to interact with. Like I said, if you have a scalar field, its gradient, the size of the gradient determines the size of the force. If the field is kind of squashed, well, you can't see it, but it's still there. So that's an important caveat. It's still there. It's just hard to see. When you're saying about this is a bit of a off the beaten route. This isn't the most popular thing. Not everyone agrees with this. And funnily enough, actually, when I had my master's Viva, one of my examiners is a dark matter person.
Okay.
So I was quite stressed going in, thinking like, oh, my thesis basically says what he's talking about is not true. He ended up not asking me anything about the gravity stuff. He just talked about cosmic voids for ages. I was a little bit disappointed because I'd done a bunch of work on all the maths and stuff, but he wasn't interested. He was just asking me about voids, and I was like, okay. But yeah, it was quite funny. Because I was like, I'm basically saying this guy's wrong. But
that's great. If scientists can have that sort of approach, that's the whole point of science, isn't it? Using evidence and stuff. Yeah. Okay, brilliant. Well, that was really interesting. I'll need to listen to it myself at least twice more once I've edited it to help me understand that a bit more. We have talked about it together. But it's really hard stuff. Some of it for me, the maths is way beyond me. But I am gradually learning, so that's part of the point of this podcast. Okay, so we've thank you very much for that, Thomas. I really enjoyed that. I hope listeners you enjoyed that, and viewers on YouTube. If you're on YouTube, don't forget to subscribe and like this video. I know everybody says that, and it's annoying, but without that, you just don't get any help with YouTube. So if you can do that, that would be brilliant. And also on Apple Podcasts, if you can give a review, that's really helpful as well. So that would be great. We've decided to abandon the idea of the dyads, haven't we, Thomas?
Sadly, yes. It was no benefit, unfortunately, even if it was fun to say every week.
It was, and it's one of those things that it sounds like a good idea. You try it, and you have to know when to give up, and so we have. So the next episode that we're going to record, it's probably the next one that you'll hear, is a psychology one, and we're going to be looking at the psychology of space travel, and in particular going to Mars. So within the next sort of decade or so, it's likely if the if the world can pull itself together, it's likely that we will have a manned mission to Mars. And so there's a big sort of whole bunch of questions around what will that do to us, or to do to the people and their psychology. So we're going to have a look at that. So hopefully that will be interesting too. It won't be as deep in maths, but hopefully it'll be interesting. And you never know, some of the people listening to this podcast might be people that go to Mars one day, because younger folk in the next, I don't know, 30, 40 years could end up going to Mars. So that's our topic for next time. Thank you very much for listening and viewing. And thank you, Thomas. See you next time.
Bye.